cars and urban vans are likely to go electric. There's going to be some different energy resources available at maritime ports, likely to go hydrogen, but this is going to be hopefully discussed later today. Rail is currently out of scope. These decisions are going to be made down line for a variety of different reasons, but this leaves heavy good vehicles as an unknown. And it also leaves it as a big chunk that can be decarbonized within the UK. So for heavy good vehicles, there are really two different options that can lead to decarbonization. So both hydrogen and electric energy systems. And there's a variety of different components within each of these systems. So for this analysis, I've looked at all the different processes from energy generation all the way to energy use. And to understand how to decrease greenhouse gas emissions in transport, this entire energy system must be analyzed rather than individual components within it. So what I'm showing here is a variety of different components that are in the different energy systems for both hydrogen and electric. So we have on the electric side, which is on the far left-hand side, or excuse me, far right-hand side, we can go through grid transmission, the recharging stations all the way to the vehicles. On the hydrogen side, hydrogen has to be produced, transported to the different refueling stations, and then used by the different vehicles. The percentages that are below each of these are the efficiency within each of these different components, and together that gives a total source to wheel efficiency for each of these different pathways. Both natural gas for hydrogen and for grid for both electric vehicles and for fuel cell vehicles are analyzed. And what you can see is that the total efficiency for battery electric vehicles is around 66% compared to that for fuel cell vehicles, which is about 25 to 30%. What this means is that these percentages represent the amount of primary energy that is used at the wheel. And to say that differently, it is the different efficiencies that dictate the amount of energy that needs to be generated upstream to meet the energy demand at the vehicle level. To show this in a slightly different way, I have here the vehicle efficiency. So this is the vehicle itself. And so the overall goal would then be to minimize the required energy upstream to be as close to vehicle efficiency as possible. And what you can see is that these different pathways actually have, advancing. There we go. They have a different level of efficiency for getting the energy to the vehicle itself. So from natural gas, we can go to fuel cell vehicles or to battery electric vehicles if we convert natural gas into electricity and then use it in battery electric vehicles. Additionally, we can go from the electric grid to either fuel cell vehicles or battery electric vehicles using either electrolysis or the grid, respectively. It's this gap between the vehicle efficiency and the black line in each of these different pathways that must be considered. So these are the big chunks that we need to try to minimize the inefficiency of the energy vector and to address in this overall energy system analysis. These gaps also have a lot of moving parts, all of which need to be held firmly together in order for this energy system of the future to be successful. So again, looking at energy generation all the way to energy use for hydrogen and electric pathways, I've identified these key linchpins, what I'm calling them. They're essentially the components that need to be held together in order for this energy system to be successful within each of these different systems. So this is the overall picture. So addressing these different linchpins individually is what this talk will be about. And for each of them, I'll assess opportunities and challenges within each linchpin based off of their potential barriers that they have to overcome and the associated risks that are that can be contributed to the larger system that they reside in. To give an example of how this analysis works, I've chosen the battery electric vehicles on an electric road system, or ERS. How this essentially works is on the top, there's a variety of different barriers that could potentially influence how successful each one of these components are, each one of these linchpins are within the overall system. I've taken a variety of different literature sources, and they have been used. I've used a rubric, which is at the end of this talk, that we can discuss later, for a risk level of low, moderate, or high for each individual literature source that I've found. When I've then combined all those together, if the consensus is that the risk level is low, the box will become green. If there's a mixture between low and moderate, the box will be blue, and so forth. An important note here is that the unknown or disputed section, which is this black and red box, this can either be evidence gaps within the literature, or that the literature has a wide variety of these risk levels associated with it. So for a battery electric vehicle, the technology readiness, which is related to the timeline of the technology to be implemented into the energy system, is relatively low, being that this technology is currently on road. The scalability, this looks at how the technology can scale with energy demand on a large scale. We'll come to a different, the resilience will look at more minute changes, but the scalability is really over a long-term energy demand change. The geographical dependence, so whether or not there is a dependence geographically on how well these linchpins can succeed. System dependence, so looking at system-wide integration. For battery electric vehicles, this has a high system dependence, and that's due to, if only part of the fleet is an electric road system vehicle, then those are highly dependent on the subsequent infrastructure. Consumer acceptance, how likely the consumers are to take on this technology. Resource requirements, so here's an example of where in the literature there is both low and moderate risk levels, so therefore this box would be a blue box. And how this is related to how dependent the technology is on natural resources. Resilience, for the actual vehicles themselves, I have excluded this box, being that the resilience is more reliant on upstream energy systems. So this will come into play as we move up the energy system. Its ability to reduce CO2, so electric vehicles are displacing, or they're removing CO2 emissions from on-road vehicles. And then the associated costs with the different technologies. And so for battery electric vehicles, the consumer and industrial costs are relatively, there's a general consensus on these, but the national costs, so what kind of help the government will have to implement, is relatively unknown. So hopefully this gives you an example of the analysis that was taken for each one of these linchpins. And then from here, we can add on to give a more holistic look at the overall energy system. So first, looking at an all-electric vehicle pathway, I have the key linchpins that'll go along the left-hand side, and again, the barriers are up on the top, and this is assessed in the same manner that I just showed. Additional to an electric road system battery electric vehicle, we can look at just battery electric vehicles, or BEVs, and their associated risks with them. Particularly here is the scalability issues, which I'm sure we can discuss this as well. Why this is unknown is due to the requirements of these vehicles, how they're going to be used, and so forth. So this is a relatively unknown part of this energy system. Moving up to the charging stations, there's a riskier consumer acceptance with this. So we see the consumer acceptance has a higher risk level due to range anxiety, and in part due to the level of decentralization being relatively unknown. So what are the requirements going to be for these charging stations? How many people are they going to have to provide for, etc. Additionally, advancements in this technology for the last 3 is extremely rapid. There's literature coming out on this every day, and therefore being included in the analysis bounds, for the technology that's available, making this a ever-changing section of this work. The electric road system itself, this is just talking about the infrastructure itself. And what I like about this is that it's relatively known. This technology has been used for a variety of different things. And so this is interesting. There is some geographical dependence, of course. Being able to electrify main chunks of the strategic road network would be a good starting point for an electric road system infrastructure, and therefore being able to reduce CO2 emissions along highly trafficked routes. Importantly here, I will also highlight, so each one of these boxes, yes, I compiled a bunch of literature and how that actually looked. So we have a consensus here where we have a solid color. And so I've taken 3 different resources here. So one from the Center for Sustainable Road Freight, one from Siemens, and one from Ricardo. And what this is looking at is the cost per lane kilometer of electric road system infrastructure. And there are a few caveats to this as to what will really influence the overall cost. But what I want the main message to be here is that roughly £1 million per lane kilometer is what this infrastructure will cost. And because this is a general consensus and it's a relatively known number, I feel very comfortable having this as a known entity within the energy system. And I think even though that it might be on the higher end of the risk level, that having a known is important when you're building an energy system. One part that is semi-unknown is that the grid capacity that are going to be required upstream of either the electric road systems or the charging stations. And this is the linchpin that gets addressed most often for all electric routes in regards to resource requirements and unknown upgrade costs. Again, the level of decentralization will influence these financial and resource requirements as well. The energy storage is also a significant component to the success of any energy system. And I'll have a slide on this in just one second, but I just want to say here that there is a variety of energy storage options that can aid in energy availability, whether that be annually, seasonally, or daily. And here I just have a quick table that lists a few different energy storage options, whether they have geographical dependence, their round trip efficiency. What this ultimately will dictate is how much energy can be sold back into the energy system. And so a higher efficiency will predominantly yield a lower cost in this energy storage system. And then the grid retention time is on there as well. So again, there's multiple options for different time scales. And I want to note here that curtailed energy, there's a movement around how curtailed energy could contribute to reduced costs in different energy systems. However, this energy will not be free. As soon as there is a market for it, as soon as people are able to start bidding on it, this is will contribute to the overall cost of the energy being sold back into the primary energy system. With that, the energy storage will address the needs of the market. It will adapt to where there is shortcomings, where there needs to be reservoirs of energy, etc. Not the other way around. There will not be an energy storage system that will try to force its way into the market. The market will address these storage needs, and because there are a variety of different options, that will help in the resilience of the energy system as a whole. I want to end on the electric vehicle pathway analysis on a positive note, and this also goes for the hydrogen side, that renewable energy is predominantly a success story where we have good technology readiness, consumers are on board with this type of technology, and we see the cost is continuing to decrease for renewable energy. So from here, I just want to note quickly that on the all electric vehicle pathway side, the technology readiness. So on the left-hand column, we see that these are mainly greens and blues, which is great. We see that we're able to move forward with this, as well as the cost being relatively stable, relatively known. And this is primarily because the technology is there, so we can make those assessments. Moving on to the fuel cell electric vehicle pathway. Fuel cell vehicles themselves, they also have scalability issues where not knowing where these vehicles will be used, how they will be used, what their specific roles will be, and if they will change at all from their current uses, that will influence how they scale up, what's required of them, their resource requirements, etc. the refueling stations for these individual vehicles, also the scalability of them being that not knowing what the tank size will be on these different vehicles, that will dictate how often the refueling stations need to be placed. And therefore the cost to consumers is relatively unknown. It is known that these refueling stations are relatively expensive, and therefore they need a high throughput of vehicles in order to make them pay themselves back essentially in a timely manner. Pipeline infrastructure, so actually getting the hydrogen from generation to the refueling stations. This is an interesting one. It seems like a great way to use current infrastructure. However, there are a lot of unknowns with this, primarily being the timeline, the energy demand flux, or how much hydrogen can actually be moved around in these pipelines, what it will cost, and the degree of utilization. So can we retrofit certain portions of the pipeline to make this work for us? Or does it need to be completely ripped out and replaced with, say, bigger pipelines to meet the energy demand that it's required to service? Also here, it's important to note that without looking both upstream and downstream of the energy use for pipeline infrastructure, development here could be wasted. And so if people developing pipeline infrastructure trying to make it use out of it are in their own little bubble, that could potentially hurt moving forward in an energy system. So making sure everyone's really connected in the discussion of how these pipelines can be used most efficiently is important. Again, energy storage, this is the same as for the other one, being that there are a variety of different options that can be used, both for hydrogen and for electric. And subsequently, if energy is stored in an electric capacity, it can then be converted through electrolysis to be used as hydrogen. So there's a variety of options there as well. Next up, we actually have the hydrogen production. So first up is the steam methane reformation with carbon capture and storage. This steam methane reformation is currently the most common hydrogen production method. However, it requires carbon capture and storage with it for it to advance in a decarbonized future. Increasing the hydrogen production for vehicle use without carbon capture and storage, which is likely to be the case from 2035 to 2050, depending on the source, will only concentrate these carbon emissions at the steam methane reformation plants. Therefore, yes, fuel cell vehicles can reduce CO2 emissions. However, if it's just displacing it and concentrating it, what harm is that doing to the overall system in general? That's something that's relatively unknown. An alternative to SMR with CCS is electrolysis. This is an interesting one as well. And one thing I do find kind of interesting is, some people claim that SMR will be the gateway for electrolysis for green hydrogen, while other sources say that electrolysis or green hydrogen will be the gateway until SMR with CCS can come online. And so having those contradictory views is interesting, and also getting on the same page with that will be important if this is a pathway that people embark down. This is also a good point to note that there's interdependencies between the barriers and with each other. So the scalability of electrolysis heavily dictates the consumer and industrial costs. So the scalability portion of it directly influences how costly this hydrogen is going to be for consumers, the capital costs that it's going to require, and therefore any subsidies that it could require as well. And again, we have the renewable energy that could lead us to electrolysis down to fuel cell vehicles. This is a relatively good success story where we see this the cost decreasing as well as it being able to scale up. Sorry, I'll back up here and just pause for a second so we can take the fuel cell electric vehicle pathway in. I hope that it's noticeable here that there are severe evidence gaps in this pathway that need to be addressed. And there are high technological barriers and unknowns that need to be hurdled for this pathway to be successful. And so constructing an energy system off of a few trusted pieces, or having only a few of these linchpins in place, could lead to a very fragile energy system. And so with that, I'll leave us up here for another 3 seconds, where you can see that the colors are a bit more ominous than with the all-electric vehicle side of things. To wrap up, we have the key system knowns. For either energy system, renewable energy is decreasing in cost, which is great, and that there's storage options available with to promote a resilient energy system. I think these are great, great progress that's been made in both of these areas. On the hydrogen side of things, as this scales up, we can decrease the cost of hydrogen, as well as it being the most similar to the current consumer engagement with refueling stations, etc. On the electric side of things, the technology is available now. And we also see that electric road systems can offer a low carbon option to high trafficked routes. So getting the strategic road network electrified can actually offer a very a low carbon future on a high trafficked route. And this will continue to decrease as the grid decarbonizes, which is also a success story. Key system unknowns. The consumer, industrial, and national costs are relatively unknown, primarily because we have a lot of other bits that need to be worked out first. Scaling up requirements. This is dependent upon energy demand, if there's a modal shift at all, any change in consumer behaviors, as well as looking at heavy good vehicles if they become more significant, used for a more specific use. So if we use heavy good vehicles in a different way than what we're currently using them, that will also change the energy demand and how we scale up any energy system going forward. On the hydrogen side of things, the green-blue hydrogen production, so steam methane reformation with carbon capture and storage or electrolysis, how they're going to aid in moving towards a decarbonized future, and which one is going to be the interim for either one, being that the infrastructure for both of these are very different. That's another component that needs to be worked out as well. The scalabilities of batteries and fuel cells. This is also true on the electric side of scaling these vehicles up. And again, on the hydrogen side, the ability to reduce CO2 emissions. So are we just relocating the CO2 emissions? Or are we actually eliminating it? And then the timeline that's associated with that as well. On the electric side of things, there's also the grid upgrade requirements that will need to be sorted out if this is a pathway that is further explored. I will say that CESI plans to dive further into these unknowns and answer these tough questions that I've just pointed out. So with that, I will take questions. Oh, I guess I'll have a panel discussion in a bit. So with that, I'll just thank you.
Thank you, Molly. Yeah, we're going to hold questions until we hear from Professor Phil Blythe from the Department for Transport. Phil's going to share his slides with us, I think.
Okay, I'm going to talk a little bit about what we're thinking about with hydrogen in the Department for Transport. I should say thank you for Molly and for CESI for supporting her to support our thinking within the DFT on the challenges of hydrogen. We've been using lots of external experts, including Royal Academy, Royal Society, Durham University, Newcastle, and Molly's team at Cambridge. And it's something that's really come onto the agenda in the last few years. I've been arguing that we should be looking more at hydrogen as a potential decarbonisation energy vector for a number of years. And I think because in the past, hydrogen's really been looked at purely from a transport point of view and probably from a single mode point of view, the economics, the carbon budget and everything else never stacked up. But since other parts of government are interested in hydrogen now, it was worth sort of revisiting that, which we started about 3 years ago. And I formed a sort of hydrogen steering committee within the department to look at that. And the reason it's important is when we think about decarbonisation, UK domestic transport emissions are around about 30% of the total emissions in the UK. And of that 30%, probably just under 90% are from road transport. And at the moment, the main objective of how to decarbonise road transport is electromobility. And I wasn't convinced that that was necessarily true for all heavy goods vehicles, for lorries and buses as well as off-road vehicles, as well as wanted to explore the opportunities that hydrogen could possibly offer for other modes, maritime, rail, and air. And the reason we have to look a bit further afield than our previous plans is when you look at carbon budgets 4 and 5, which are the two dotted lines you can see, they're way below what we think we can achieve with the current DFT plan, which is the green line. So there's some massive challenges there. We've got to decarbonise more in transport, and we've got to decarbonise road transport the most, because that is the significant proportion. So looking at what we can do with electromobility, which is critically important and clearly being proven for cars and small vans, there's in the grey area of what do we do for large vehicles? Is it part electric, part hydrogen, and the like? And part of the work that Molly's been doing is looking at some of the technical, scientific, and economic issues around that. But one of the other reasons why we're quite interested in that, this is some graphs that Grant Wilson from Birmingham send me on a regular basis. This is showing the energy use in the UK. The blue line, which sort of peaks and troughs winter, summer, is our natural gas. The red line is our electricity generation, which has some seasonal variation, but not very much. And the grey line above the red line is the amount of fuel used in transport at the moment, mainly petrol, diesel, oils, and the like. And as you say, that's a massive amount of energy. And if we're going to decarbonise that and replace it by electricity, that's a massive increase in both the generation and the distribution of electricity. So if we can look at other modes that might help to make things resilient as well, that's important. And these are some of the arguments why we in transport have begun to look at hydrogen, but clearly other sectors, particularly big industrial processes, which require heat and or big energy, shall we say, and homes, heating and cooking at homes, suggests that hydrogen will have a role to play going forward. And if it's being generated for more than one sector, then there's scalability and cost reductions that are possible. And so when we look at transport, we think about battery electric, which is an obvious decarbonisation vector. We think about fuel cells. We think about route electrification, which Molly's just been talking about. We think about hybrid vehicles that run on battery and other things. That could be petrol, diesel, or fuel cells, for example. And we also, particularly for things like aviation and potentially other large transport vessels, synthetic fuels, which could be created from sucking carbon and air out of the air and converting it into a fuel, which is possibly a long-term solution for aviation. And there's opportunities in all the modes, but I just noticed here when I put the modes up, I didn't include aviation, where I think there are real opportunities for hydrogen as well. So what are we thinking about? I mean, obviously in government, we've got to think about the production and whether hydrogen can actually scale up and provide hydrogen at a cost which is affordable to transport. Maybe not now in terms of cost, but in the future to replace, what is akin to diesel or petrol or electric, and how that hydrogen is produced. And Molly's gone through the two main opportunities, which are through steam methane reforming with carbon capture, ultimately blue hydrogen, and electrolysis from renewable electricity. And there's an awful lot to think about there, and there's an awful lot to think about how that's connected into the wider energy system. But from a transport point of view, can you deliver the amount of hydrogen we would need for the modes? Is it scalable? Can it be done at cost? Will it be green in the long term, even if it may be blue or even, dare I say, brown hydrogen in the early stages to prove the concept, and at a cost that is acceptable to transport? And to do that, we need to understand the maturity of hydrogen technologies. understand the duty cycle of vehicles that may use hydrogen, and really compare that to things like battery electric. You know, battery electric on the face of it is clearly more efficient than hydrogen because there's an additional energy conversion in the process. But if you've got a bus or a lorry with 3 tons of electric batteries on there, and you put that into efficiency calculations, what does that mean? Does that mean hydrogen steps up a little bit more? Do we need to think about it just from a resilience point of view? Lots of questions in that particular space. And also, would it be a national system or would it be place-based to the places in the UK where there is a obvious hydrogen economy? And understanding how that fuel mix and the pros and cons of bus manufacturers and bus operators investing in electric buses or biofuel buses or hydrogen buses, same for HGV, same for other sectors, is really, really important. So understanding that well to wheel and understanding the economics of that are really, really important, but not just now, where clearly hydrogen is regarded as almost as a new technology, but in the future, when you're comparing hydrogen that's been much more industrially developed and innovated, how does that stack up to battery electric operation, for example? And at the moment, the UK position has been quite unclear on hydrogen because different departments have been thinking about it in different ways. We started investment in small trials of hydrogen fuel cells and infrastructure a few years ago, and they're beginning to ramp up a little bit now. But there's still more to do. There is the opportunity for hydrogen bus cities along with towns, along with electric bus towns. And there's some new activities like the Teesside Hub, which I'll talk about later. But what we're trying to do is gather the evidence to understand what role hydrogen will play and what support it needs if indeed we are going to use hydrogen, or indeed is it a red herring for different modes that may impact on that. The only mode that's come out clearly stating that hydrogen in one form or another, whether it's direct hydrogen through ethanol or more likely through ammonia, is maritime. They're clear that hydrogen is their fuel of the future. Here are some of the places that really have hydrogen infrastructure at the moment, and included on there is Teesside, which has some interesting propositions. And as part of a research and development package we developed last year, Teesside is playing a major role in helping that hydrogen will play in transport. What I would love to see in there is places like Boies as a hydrogen spoke. It's got the renewable energy catapult bringing the electricity in there, potential for a new railway line, Boies Ashington and the like. And that would, I think, be a really interesting place to play with hydrogen in the Northeast, for example. What we're doing at the moment, we've announced various things in decarbonisation, everything from cycle links to investment in bulk hydrogen to look at decarbonisation. And, you know, we're not the only country doing this. There's massive investments going into Japan and Germany in hydrogen. And I think that was reflected as well in the EU's clean, in the EU's announcement of this 1 billion programme in the EU Green Deal on hydrogen. In the UK, to reflect the interest in hydrogen, we set up the Hydrogen Advisory Council chaired by the Secretary of State from Boies to really advise on the business and scalability aspects of hydrogen. The CSAs have set up a network under the Net Zero Innovation Board to really look at it from the science and technology and engineering challenges and joining up challenges across departments. And if you remember in November 2020, the Prime Minister announced his 10-point plan on green tech and green recovery. And in that, it mentioned things like small modular reactors, nuclear reactors that could be invested in, all the investment going into electromobility, but also the announcement on hydrogen and specifically on the Teesside hydrogen transport hub, which is something that I've invested in at the DFT to help us understand all those unknown questions about hydrogen in transport. So the Teesside hub has 2 phases. We funded a master plan which was developed over the second half of last year, which comes up with how the buildings and the infrastructure and the hydrogen generation with electrolysis that would be needed to really make Teesside a sustainable hydrogen hub, identify the number of vehicles and types of modes that would benefit from hydrogen. And that's really looking at the completion of the infrastructure and going forward from 24-25. But what I'm really interested in at the moment, this is where maybe some people on the call and CESI can help, is as part of this, we will receive 3 million in the spending review to take forward the hydrogen hub at Teesside in the next financial year, March 21 to March 22, and really get some of the demonstrations, get some of the science and research and the questions that we need answering about, is hydrogen a suitable fuel for different transport modes, to be answered then. So I think there's a real opportunity to the research community to support that. These are some of the things we see within the hydrogen master plan and what we're doing. It's really understanding all the cross-sector stuff about hydrogen, safety, security, standards, distribution, production, understanding what it means for different modes of transport and how that can be brought together to bring the amounts of hydrogen required by transport to points where it becomes economically viable. It's also looking at all the research that's needed to answer those key questions. And that's really important to us, because all the decisions we make on decarbonisation are evidence-based, and clearly, because we don't have much hydrogen activity within transport at the moment, we don't currently have much evidence from the UK. We don't have the opportunity to test and trial. We've got a few trains, we've got 1 or 2 ships that have been converted, we've got a few planes, and we've got some cars, vans and lorries, but in very small numbers. So we really want to try and stimulate the market to deliver this stuff to us, but we want to just not just think about the vehicles, which is normally how DFT think, but also about the infrastructure. We recognize that the energy infrastructure and the systems integration of the energy infrastructure is critically important going forward with decarbonisation, and particularly for transport. So how does the electricity, the hydrogen and other infrastructures fit together to deliver the energy needs for the UK, and also understand all the behavioural user acceptance side of hydrogen. To do that, I funded a transport decarbonisation R&D roadmap last year. This was done by a number of partners, including RAND, Mott MacDonald, and UE, Glenn Lyons. For this, we sort of roadmapped all the different opportunities for decarbonisation of roads. So we looked at hydrogen and its variants, battery electric, route electrification, bio and synthetic fuels, and really began to understand what were the likely modes and what were the likely scales of demand for energy in those places. So that's critical. That's feeding into the transport decarbonisation plan, which we're currently drafting within the DFT. We produced the Setting the Challenges document in March of last year. And if you read that, it's quite ambitious in what we're trying to do. It's trying to be, in the typical government way, technology neutral, which means it doesn't pick winners. What we need to do is begin to pick those winners, because we cannot hang around for 10 years before someone says yay to hydrogen or yay to synthetic fuels. And so the full plan will be out in March of this year. There's lots of R&D in there. There's lots of links into UKRI challenges and the like. And I see a role for a CESI or the son or daughter of CESI to really play a key part in making sure we understand that energy systems integration aspect of delivering, not just for transport, not just for hydrogen, which will have a role to play, I'm confident, in certain modes of transport, but also in the wider energy system and mix of the UK. So look, that's just a very brief whiz through some of the things we're thinking about. I think the Teesside hub being the focus for R&D and really answering those unknowns we have around hydrogen is a real opportunity, and then growing that into a wider capability, I think, in the northeast of England is an ambition I have. So, Laura, I'll finish there.
Thanks very much, Phil. In the background of our panel, I'm just going to share my screen so that we get a little bit of, if I could just quickly ask the panel to introduce themselves. I have got a slideshow with your job titles so that people can see who you are, but if we start with Molly, introduce yourself, because there are some people who've just arrived and maybe missed the start.
Yeah, not a problem. I am Molly Haugen. I am a research associate in Adam Boies' group. I work primarily on energy system analyses. And yeah, so I'm excited for this panel to get some good feedback.
Yep, and Adam? you want to introduce yourself? You're on mute at the moment.
Sorry, yep, Adam Boies. I'm head of the Energy Group in the Department of Engineering at Cambridge, and a member of the Center for Sustainable Road Freight.
Thank you. Sarah?
I'm Sarah Walker. I'm Director of the National Centre for Energy Systems Integration.
And David, please.
I'm David Flynn, a Professor of Smart Systems at heriot-watt. I'm one of the Associate Directors working with Sarah and the team at CESI, and I'm also the Academic Lead of the Reflex project in Orkney.
Okay, if anyone has any questions for the panel about what Molly's research or Professor Blythe's comments, can I ask you to put your questions in the chat window? First of all, put in your name and the organisation you're from, and we'll start off some discussions. Does anyone from the panel have any comments on Professor Blythe's Teesside hydrogen hub?
I can maybe just comment that I think the integration piece that Phil mentioned is really important. So we're trying to better understand in CESI what the potential trade-offs are of different energy vectors and their different uses. So if hydrogen is an appropriate route for maritime, then what does that mean in terms of the availability of hydrogen for other applications such as domestic heating or other transport applications? So integration is really quite important to try and understand those trade-offs and to look beyond single applications or single vectors to better understand how the energy system as a whole could be made more effective.
Thank you, Sarah. We've got two questions. The first one is from Professor Skelly from Durham University for Molly. He said he was interested in the results she had for the linchpin analysis, particularly why the fuel cell and the electrolysis were not green for TRL. These are fully commercialised in his opinion, and why electrolysis was red for consumer acceptance. He just asked if you could explain that a little.
Can I just ask for the definition of TRL?
Oh, sorry, technology readiness level. So where it is ready for, so a low TRL would be something that is blue sky thinking that might only be considered in university, whereas a high TRL would be very commercially ready and ready for market.
Yeah, great, thanks. So electrolysis, yeah, that's a great question. So the fully commercialized electrolysis plants that are available are mainly alkaline electrolysis, and you can please correct me if I am incorrect in this. For fuel cell vehicles, they need to primarily be, well, high purity, which is great, but for renewable energy, to be attached to renewable energy, polymer exchange membrane electrolysis is often the more cited electrolysis that is paired with this due to the intermittency of it. And these are a lot slower on the commercialization of them as well.
Okay, thank you.
Yes, you are correct. There are very commercialized electrolysis machines out there, but for renewable energy system, PEM electrolyzers are most common, and they're not as commercially available on the scale that's needed.
And we have a question from Professor Gross from UKIC, and I'm guessing it might be to Phil Blythe, but maybe to the panel as well. Is the era of not picking winners over?
In theory, yes, but I do find that government departments will sit on the fence for as long as they can. The only winner that's really been picked in decarbonisation is electrification. If you can electrify road transport, that's great. Anything else is a challenge, because they've put a lot of eggs in that basket. And that's why we're trying to gather the evidence to show that there are parts of the road transport network which may benefit from hydrogen, either because of the size of the vehicles or the duty cycle doesn't suit battery. And also not forgetting that off-road vehicles, particularly things like construction and mining and farm vehicles, They require a lot of power and very rugged, and batteries don't seem the right option for those either. But yeah, I think, you know, we're in a climate emergency. I think we should be getting to the point where we deliver the evidence quickly so we can pick winners. And certainly with the view of Boies in terms of when they're going to make key decisions on hydrogen and investment in large scale production, I think it's too far away. If we're going to make sure that if we are going to go down a hydrogen route for certain sectors, that hydrogen is ready and available at a time that's needed. And also what that means to the electricity network and the like, to deliver the decarb electricity to make the hydrogen, for example. So yeah, I think there is an urgency to start making decisions.
I hope that answers your question somewhat, Rob. Yeah, thank you. There was a question in the chat from Professor Heron from Newcastle University, who runs Zero Carbon Futures. He's asking if the decision of the vehicle manufacturers really that will decide which technology wins, and we've got no control over them, question mark. So what does the panel think of that?
You want to go again? I think, you know, vehicle manufacturers did not want to move away from petrol and diesel. Very easy to make those cars at a very low cost. Those cars evolve over 20, 30 years with very little R&D, so they can make a lot of money out of it. They were pushed kicking and screaming towards electromobility, and only in the last couple of years have they realized that that's inevitable and that's where their business models need to go. Obviously, infrastructure has been put in place for electromobility. Infrastructure has not been put in place for hydrogen. So we're really going back to somewhere in like 2009, where we were with electric vehicles with no infrastructure, a dirty electricity from the grid, and a leap of faith that the infrastructure and the decarbonisation would come. That's all needed for hydrogen, which is one of the reticence for looking for a second energy vector for transport, well, particularly road transport decarbonisation. But I genuinely think we need to go there.
Okay, thank you, Phil. Anyone else want to comment on that?
Well, maybe one additional comment. You know, in areas like electric road systems that the Center for Sustainable Road Freight is a proponent of, you know, there's a large interplay with, you know, not only the vehicle manufacturers but the infrastructure developers, and so those have to work in concert. You're not going to produce vehicles for an electric road system without one. Even that, it's even more acute for electric road systems than it is for charging infrastructure. So that will be an important interplay between those two sectors. And it's not clear at all who pays for that. And so, you know, who pays first is a critical aspect in that evolution.
Okay.
If I could just briefly add to that point from Adam, and it's a really good point raised by Colin, is I think the automotive industry, the vehicle manufacturers, are very aware of the cards they hold and the cards that the network operators and policymakers hold. So in conversations I've had personally with companies like Tesla, they know in the UK instance, the kind of the bearer of demand is going to be the network operators. And they know that the policy has been set, the pressure is there, and the regulation of our market really does put the spotlight onto the network operators on creating infrastructure that enables this. Albeit intuitively, you think, you know, with the enabling infrastructure, you have more products and services to sell in this market. So surely you will be part of that evolution. But the feedback I have and the evidence I've seen is they are quite happy at this moment in time for the UK to prepare that infrastructure. With respect to beyond the UK, as we know, there's going to be issues with commercial freight and connectivity across nations. But for purely the UK instance, I do think, rightly or wrongly, we're going to be looking to the network operators and the public purse driving this one forward.
Okay, well, thank you for that. I see Colin's joined us, but I'm going to move on to the next question because we have another couple, but we'll maybe come back to it, Colin, if you've got some additional insight But we've got a question from Upa from Loughborough University. Again, just a little comment on Molly's presentation round about the emissions associated with electrolysis.
Yeah, I can just comment on that really quickly. I think there is that possibly just didn't show up on the slide, but I have it as a blue box. So there's, depending on where the energy is coming from, there should be a CO2 emission, and then that will ultimately dictate what the level of CO2 reduction would be in that energy system. So I have accounted for it, and I apologize if that didn't pop up on the screen.
Okay, thank you, Molly. We've got one question from industry. So Adrian Wilson from the Energy Workshop. Molly mentioned constrained electricity. So this is a question for the whole panel, really. Does the panel think that constrained electricity is or will be sufficiently available to make investments in electrolyzers work economically? I honestly didn't pay Adrian to say this, David, but he's asked if the Orkney Reflex project is an example. So here's something I prepared earlier. For anyone who's not aware of the Reflex project, I'll let David quickly introduce it.
Thank you for that, Laura, and thank you for the question, Adrian. And I mean, I think this relates back to some of the prior questions about learning some hard and fast lessons through energy system integration. In the instance of Orkney and the Reflex project, as well as I should give them credit as well, there are other associated projects. Surf and Turf is another one with a fantastic name, where we have seen the benefits in terms of heavy machinery, maritime transport, aviation with respect to the role of hydrogen. Where we have faced challenges in the instance of the hydrogen economy in that specific energy system topology is actually in having some sufficient energy demand with respect to heat and the role of hydrogen in terms of the enabling technologies. Without sufficient demand, the remaining useful life of these hydrogen CHP systems that we have is uneconomical. So in the unique instance of what is a community of 22,000 people, some aspects of energy services have been slightly insufficient for the business use case in hydrogen, prospered in others in terms of, as I say, maritime, aviation, the agricultural economy they have. But that I anticipate would not be the case when you look at something more industrialized, such as possibly the Teesside cluster. I hope that answers your question.
Thank you very much. I'm very conscious of time, and we've got a bonus presentation planned from Professor Boies about the carbon.
No, please go ahead with this. I mean, I think it's more important that we have this discussion. Yep.
Thanks very much. I think we can still do it. And I'm conscious that some of the panel may have new meetings to go to. So by all means, if I'd like to, before anyone will leave, I'd like to thank everyone who's presented today, and especially Molly. That was very interesting and exciting, and it gives us even more questions to answer in our research. So thank you very much for that work, and thanks again, Professor Blythe, for providing the DFT insight. Yeah, lots of questions still to answer, and it's a really exciting time, I think, for this area. I'm happy to keep the panel open because this is me for the next 15 minutes, but if there's any more questions, let me just check if anything came in. I'll just stop sharing my slides, actually. Okay, so if there's any other questions in the chat window, I don't think there are. Do you see any other questions?
Well, there have been a number that have kind of popped up, maybe 4 or 5 here.
Okay, give me 2 seconds. Okay, I'm up to speed now. Yes, Professor Greening from heriot-watt. Could the panel explain why hydrogen remains an option for road and rail? There may be a case for using hydrogen for maritime and maybe aviation. although biofuels would seem more attractive for the latter. Would this be a better mix?
Yeah, it's a good question. Maybe I'll hand over to Molly, but first of all, just say, you know, some of the costs that she presented perhaps gives a little bit of an answer as to why ERS is a little bit expensive, but hey, so are a lot of the other options. But I suppose what we're trying to understand with CESI is if hydrogen's going to be relevant for other sectors and therefore becomes more available and the technology costs reduce as a result of demand in other sectors, then is there potential for hydrogen to become a sensible option to consider as part of these transport discussions, particularly for applications where you've got certain power requirements or certain range requirements that mean that electric options are less appropriate compared to hydrogen. That's not to say that either technology is impossible, but I think there's this interplay with other sectors that means that we don't want to discount hydrogen completely. And that's why Phil was mentioning that hydrogen had come back on the agenda, because other government departments were thinking about hydrogen as relevant for other applications, and therefore potentially that could mean that hydrogen costs came down, or that excess hydrogen from industrial applications could be used in other end uses. But perhaps Molly could comment on the ERS question as part of that.
Yeah, I can happily, I'll happily answer, give a comment on it, I guess. I do appreciate the stance I get to be in, right? I get to look at all the different research and present what other people have done. I think there is a role for an electric road system here in the UK where we can decarbonize a big component of it. Like Sarah mentioned, there could be interplay between other sectors. I guess as far as why hydrogen keeps popping up, there's some attractiveness to it, but for the on-road portion of it, which is where I focused, for me, it just seems like there is a lot more unknowns and uncertainty around that as well. So, you know, if there's an interplay between other sectors, that could very well be, I think, for the on-road sector, just looking at that individualistically, I think, you know, there could be a more attractive solution.
Could I add to that, Laura? I think one of the challenges is that hydrogen is just beginning to be considered seriously for mainstream transport. Whereas we started with electromobility 12, 13 years ago, and we had leaps of faith then in terms of the electricity grid was not very carbon clean. You know, we're talking about 700, 800 grams of CO2 per kilowatt hour. And the price of electric batteries were sort of $1,500, $1,600 per kilowatt hour of lithium ion storage. We knew that would change, and we invested in it. The challenge now is persuading people that there is a role for hydrogen and delivering that evidence, and then investment in a second energy supply network for transport, and particularly road transport. So there's a big leap of faith to be had. And if you compare like for like at the moment, hydrogen will never stack up. But you know, like with electric batteries, have gone down from $1,200, $1,500 per kilowatt hour of storage down to just under 200 now. I'm convinced that with the right steer from customers and from government, the hydrogen suppliers of fuel cells, of vehicles, of electrolyzers, of storage, and of distribution systems will innovate and deliver at much lower cost than they can at the moment. But I think the window is quite short. But I also think when you look around the UK, there's lots of really good manufacturing and innovation in hydrogen. We have a proper hydrogen industrial cluster that can deliver all the elements in a way 10, 12 years ago we didn't with electromobility. So it's worth considering. It may be, you know, based on the work of Molly and others, that we find we're going down the wrong road. But I think the opportunities to explore that are great. I'd just like to say something to David. I think the work going on in Orkney is fascinating. We've been following particularly some of the work on maritime and our maritime team at Dept are learning from that, and I think that's really important. But again, it's going to take time for the numbers to stack up and the economics to stack up, and that, you know, the role of government should be to deal with things when the market is not there yet, or the market is broken. And you know, when we're at that early phase, it does need support.
Thanks very much for that. Just one last question. I think we'll need to let people get on with their lives. But one last question maybe for me, and it maybe answers some of these concerns, is what do the panel think about the solutions for place? We talk about hydrogen, we talk about Teesside and places like Orkney. When we talk about electrical road systems, are we talking about very heavy utilised, in fact Molly did mention very heavily utilised road routes. M25 comes to mind, but it's maybe not something that's maybe required in the rural area of Northumberland, for example. So while we can't afford everything, do you think that different solutions will emerge in different locations?
Yes. I think it's likely that we will see more interest in using hydrogen across different uses where there is an industrial pull, first of all, for hydrogen demand. And so that's why Teesside is quite interesting for us to look at as a research community. So I think there's an interplay there with industrial demand in terms of place, but I also think in terms of renewables, that different technologies and different renewable resources are more prevalent in certain locations around the UK, and so it might seem like hydrogen with offshore wind is more appropriate for the North Sea coastline, for example. And so I think we will see some place-based solutions. I don't think I don't think we'll get a one-size-fits-all, and that's why research like on Orkney and some of the local energy systems research, it is interesting to see not only how does that work from an energy systems point of view, but how does that work from an end user point of view, and how do we enable the energy end user to get the level of service that they need.
Yeah, thanks very much for that, Sarah. But an interesting question there from Professor Fan from Keele University, and it's a question to the panel about, can the panel comment on the emerging low-cost scalable electrolyser, for example, the Enapter system, and impact on transport? So if, and kind of paraphrase a little, if electrolysers were cheaper, would this be a different discussion?
From my perspective, probably yes. And I know companies like ICM are looking for more projects where they can use their electrolyzers, which will help them industrialize and reduce cost. There just aren't enough of them. There aren't enough of those projects out there at the moment. So the cost of the electrolyzers are eye-wateringly expensive. My view is that they will reduce over time if the demand's there, or if there is a strategy that says the demand will be there at some time in the future. Please invest and solve these problems.
Maybe to offer my view on that, I think there's a lot of work to be done on decarbonizing the hydrogen used industrially, and I think that's where these low-cost electrolyzers will be used first. Those hydrolyzer or the electrolyzers, if you look at where commercial facilities, industrial facilities that use hydrogen, they're always right on a hydrogen pipeline, and so you know, and those are SMR generated hydrogen, and so the real opportunity for low-cost electrolyzers, I think, to penetrate the market is perhaps not in the transport sector, but in the heavy goods sector. I still, you know, Molly's analysis holds that it'll always be less efficient to go to hydrogen from electricity and then back to a fuel cell vehicle that's fundamental and independent of even zero cost electrolyzers. So the case would need to be made on some other basis from that perspective.
Okay, well, I'm going to have to wrap up there.